In this video, I will talk about the Godunov's method. This is one of a very famous methods in finite volume method. So what happens in this method? Let me just talk about the how finite volume method works. We know that to find out the quantity, we write Qn I, maybe n plus 1 I, 1 over delta x, xi minus 1 half, xi plus 1 half over the cell, and we write it like this qxt n plus 1 dx. When we take an average of the quantity q over the cell, then we have the value qn plus 1 I. That was all we did in our previous lectures. The smarter way, one of the smartest way, the Godunov's method introduced in 1959, he said that if you want to calculate q and capital Q n plus 1, this quantity over here, then replace this q with piecewise polynomial. With piecewise, replace this with piecewise polynomial. You can do that, polynomial. Okay. It is similar to what we do in numerical analysis for trapezoidal rule or Simpson's rule. So the one of the simplest approximation is when we have q x t n plus 1 is constant value. Remember that it is called a reconstruction. We reconstructed our variables from q by replacing this q with q tilde, some linear polynomial or constant. It can be a constant. If it is just a constant, we write it like this. So that's how we actually define the Godunov's method. It is just a simple thing. You just need to replace this q with some piecewise polynomial. It can be a constant, since in polynomial you have constants. You can write it as linear polynomial and so on. We will probably talk about that in future video, linear polynomial. Okay, suppose we replace this q tilde q tilde x t n with constant value, which is q n I, x belong to cell I. And similarly, if we have, for example, q x t n plus 1, we just replace that with a constant value q n plus 1 I, x belong to ci. Such thing is called the reconstruction of numerical method. Okay. Now the question is, what will be the numerical flux in that? This quantity, remember that in numerical method, for example, we have qn plus 1 qn I minus delta t by delta x. We have fluxes I plus 1 half fn I minus 1 half. This numerical method has two components. One component is the variable and another component is the fluxes. These are the fluxes. So how do we write flux in the Godunov's method? We know that we already defined the flux fn I minus 1 half by taking average over the delta t, tn to tn plus 1 f of q xi minus 1 t and dt. So what does the flux mean? We know that we have to replace this Q with some piecewise constant or polynomial. Okay, so we can replace this with Qi minus 1/2, or it will be written as Fn I minus 1/2 is equal to 1 by delta T, Tn to Tn plus 1, and we can replace this with Q steric, or maybe Q tilde, Q steric Xi minus 1 T dt. And you can also take the values Tn plus 1. We have flux maybe Q vector. It is a kind of symbol. We have Qni minus 1. You can take the value Qni minus 1 and Qni dt. Okay, that's what we have over here. Since f will be a constant, and you can just integrate that, since the flux is constant here. Flux is Q is constant. We are discussing the Q is constant. So if it is just a constant, for example, Qn I, something like that, then it will come outside of the integration, and after integrating, we get f, the same flux over here. So Fn I minus 1/2 will be equal to I minus 1/2 will be equal to F Q, which depends on the values from Qni minus 1 or Qni, so on. So it means that at Xi minus 1/2, we solve the Riemann problem. You can see that for I minus 1/2, we already had, for example, this is I minus 1/2, and we earlier know that we either can use Qni minus 1 value, or we can use Qni. So for I minus 1/2, we have a jump in the solution. So it is called actually a Riemann problem. If we have Qni at the cell, then this is a kind of jump over here. So you are solving, by Godunov's method, you are solving Riemann problem at every cell. Here, for example, then again here, then again, you are solving Riemann problem. This is your first Riemann problem. This is your second Riemann problem. This is Riemann problem, so on and so forth. So you are solving actually a Riemann problem. This is called the Godunov's method. Okay. I hope you got the point. And the next thing we want to use maybe in the next video is to write the waveform of this Godunov's method. Thank you for watching.